Let me start today with a simple question. Imagine I hand you a spoon, and I ask you to scoop up just one small spoonful of a certain material. An ordinary teaspoon. Nothing fancy. How heavy could that little scoop possibly be? A few grams, right? Well, hold that thought, because the answer I am about to give you is one of the most absurd numbers in all of science. That single teaspoon would weigh about 1 billion tons. Not 1 billion grams. 1 billion tons. That is heavier than every single human being on Earth, all 8 billion of us, piled onto one spoon at the same time. And no, before you ask, this is not a new diet plan. It is a real substance, and it exists right now, in stars scattered across the night sky. This impossible material makes up an object called a neutron star. It is what remains after a giant star dies in a supernova. And it might be the single most extreme thing in the entire universe that is not a black hole. Tonight, we are going to shrink an entire sun down into the size of a city, spin it 700 times a second, wrap it in a magnetic field strong enough to rip you apart from the distance of the moon, and then, at the very end, find out where the gold in your jewelry actually came from. Neutron stars are, frankly, ridiculous. Everything about them sounds made up. And yet, every strange fact I am going to tell you tonight has been measured, confirmed, and in some cases won the Nobel Prize. So let's begin where every neutron star begins, with the violent death of a much bigger star. If you saw our last video, you already know how this story starts. A giant star, at least 8 times heavier than our sun, spends millions of years fighting a losing battle against its own gravity. And when it finally runs out of fuel, its core collapses and the outer layers explode outward in a supernova, one of the brightest events in the entire cosmos. But tonight, we are not interested in the explosion. We are interested in what gets left behind, right at the center. Because while the outer layers are blasted into space, the core of the star is doing something almost impossible to imagine. It is being crushed. When the core collapses, gravity squeezes it with a force beyond anything in our everyday world. Something larger than the Earth is compressed down to the size of a city in less than a second. And under that unbelievable pressure, the atoms themselves simply give up. They can no longer hold their shape. To understand what happens next, remember what an atom is normally like. At the center is a tiny nucleus, and far away from it, electrons orbit around, with a huge amount of empty space in between. An atom is mostly nothing. If the nucleus were the size of a marble, the nearest electron would be hundreds of meters away. That emptiness is what gives ordinary matter its size. But in a collapsing core, gravity crushes that empty space out of existence. The electrons are jammed so hard into the protons that they fuse together and turn into neutrons. The whole star's core becomes a single, solid ball of neutrons packed shoulder to shoulder, with no gaps left at all. That is where the name comes from. A neutron star. It is, in a way, one gigantic atomic nucleus, about 20 kilometers wide. And let's really sit with that size for a moment, because it is the key to everything. Our sun is about 1.4 million kilometers across. You could line up 109 Earths along its face. A neutron star takes more mass than that entire sun and squeezes it into a ball roughly 20 kilometers wide. 20 kilometers. That is the size of a city. You could drive across a neutron star faster than your morning commute. Take the entire mass of the sun, more than 300,000 Earths, and fold it up until it would fit neatly inside the city limits of, say, London or Los Angeles. That, right there, is a neutron star. And now the billion-ton spoonful starts to make a little more sense. So let's finally talk about that density, because it really is the headline act. Everything around you, this table, your hand, the air you are breathing, is mostly empty space. Remember, atoms are almost entirely nothing. If you could squeeze all the empty space out of every atom in a human body, the leftover matter would be smaller than a grain of dust. A neutron star is what you get when nature actually does that. All the empty space, gone. Just pure, solid nuclear matter, packed as tightly as the laws of physics will allow. Its density is around 100 trillion times greater than water. There is nothing else like it that you could ever hold, or, well, that would hold still long enough to be held. This is where our teaspoon comes back. Scoop up 1 spoonful of a neutron star, and it weighs about 1 billion tons. Let me try to make that real. Picture the largest mountain you have ever seen. Now imagine crushing that entire mountain down until it fits on the tip of a spoon. That is the weight we are talking about. A mountain in your hand. Of course, you could never actually hold it. The instant that spoonful left the neutron star, with no crushing gravity to contain it, it would violently explode. And even if it somehow held together, its own gravity would rip the spoon, your hand, and most of the surrounding neighborhood down toward it. So please treat this as a thought experiment only. Do not try to bring a neutron star home in your kitchenware. All that mass packed into such a tiny ball does something dramatic to gravity. On the surface of a neutron star, gravity is roughly 200 billion times stronger than it is here on Earth. Your weight there would be measured not in kilograms, but in something more like the weight of an entire mountain range. Here's a way to feel it. If you dropped a single marshmallow from just 1 meter above the surface, it would slam into the ground, moving at over 1,000 kilometers per second. A soft, harmless marshmallow would hit with the energy of an atomic bomb. On a neutron star, tripping is not embarrassing. It is instantly, catastrophically fatal. So, watch your step. And a neutron star is not just a featureless ball. It actually has a structure. On the outside is a thin atmosphere of hot plasma, only centimeters deep. Below that is a solid crust of crystallized matter, incredibly rigid, billions of times stronger than steel. Physicists even think that deeper down, the matter arranges itself into bizarre shapes they have nicknamed nuclear pasta, sheets and tubes like lasagna and spaghetti. Yes, that is the real scientific name. Now we come to my favorite part, because a neutron star does not just sit there being heavy. Many of them spin, and not gently. To understand why, think of a figure skater pulling in their arms to spin faster. When the giant star's core collapses, it shrinks enormously, and just like that skater, it spins up to an incredible speed. A young neutron star can spin dozens of times every second, and as it spins, its powerful magnetic field channels beams of radiation out of its 2 magnetic poles, like 2 lighthouse beams sweeping through space. If one of those beams happens to point at Earth, we see a flash. Then the star turns, and it goes dark. Then the beam comes around again. Flash, dark, flash, dark. A perfectly regular pulse. We call these spinning neutron stars pulsars. And the story of how we found them is wonderful. In 1967, a young graduate student named Jocelyn Bell was studying signals from her radio telescope when she noticed something strange. A signal that pulsed with almost impossibly perfect regularity, ticking away like a cosmic clock. Nothing in nature was supposed to be that precise. The signal was so regular, in fact, that the team could not immediately rule out that it was artificial. A message from an alien civilization. Only half joking, they labeled that first mysterious source LGM-1, which stood for Little Green Men. It turned out not to be aliens, of course. It was the first pulsar ever discovered, a dead star, spinning in the dark, keeping better time than most of the watches on Earth. And some of these pulsars spin at speeds that break the brain. The fastest one we have ever found spins 716 times every single second. Let that sink in. An object more massive than our sun, wider than a city, is whirling around more than 700 times in the time it takes you to say the word neutron. Its surface is moving at nearly a quarter of the speed of light. It is the fastest spinning known object in the universe. These pulsars are so steady that when they do change, we notice instantly. Every now and then, a pulsar will suddenly speed up just a tiny bit, in an event astronomers call a glitch. We think it happens when the star's incredibly rigid crust cracks and shifts under the strain, a kind of neutron star quake. A city-sized starquake, on a surface where a millimeter-high bump counts as a towering mountain. And here is something beautiful that came out of all this. Because pulsars keep time so perfectly, scientists realized we could use them like cosmic lighthouses to navigate. In fact, when we sent the Pioneer probes out of the solar system, we engraved a map on them, marking Earth's location relative to 14 specific pulsars. If an alien civilization ever finds it, that map of ticking dead stars is how they could find their way to us. So neutron stars are unbelievably dense, and many spin at ludicrous speed. But there is a special class of them that takes the extreme even further. We call them magnetars, and they hold a record that is genuinely hard to comprehend. They are the strongest magnets in the known universe. Let's build up to just how strong. A fridge magnet has a field of about 100 Gauss. A powerful hospital MRI machine, the kind that warns you to remove all metal, is around 15,000 Gauss. A typical neutron star is already 1 trillion times stronger than that. And a magnetar? A magnetar's magnetic field can reach 1,000 trillion Gauss. It is, by a wide margin, the most powerful force of its kind anywhere we have ever looked. A field that's strong does not just attract metal. It warps the very atoms of matter, stretching them into thin needles and rewriting the rules of chemistry itself. If a magnetar were placed halfway between the Earth and the Moon, its magnetic field would wipe the data off every credit card on the planet and mess with the atoms in your body. This is the universe's polite way of saying, please, do not touch. And a magnetar's power can erupt with terrifying suddenness. On the 27th of December, 2004, a magnetar called SGR 1806 exploded with a starquake, a violent crack in its crust unleashing its magnetic energy. In just 1/5 of a second, it released more energy than our sun puts out in 250,000 years. And here is the truly incredible part. That magnetar was about 50,000 light years away, halfway across our galaxy. And yet, when its flash of energy reached us, it was strong enough to physically disturb the upper atmosphere of the Earth. A single star, unimaginably far away, briefly reached across the galaxy and touched our planet. From 50,000 light years, it still managed to knock on our door. Now for the part of the story that I think is the most beautiful, and it connects these strange dead stars directly to you. Stars very often come in pairs, orbiting one another, and sometimes both stars in a pair end their lives as neutron stars. So you end up with two of these city-sized, billion-ton objects, locked in orbit, circling each other in the dark. But this orbit is not stable forever. As they whirl around each other, they stir up ripples in space itself, and slowly, over millions of years, those ripples carry energy away. The two stars spiral closer and closer and faster, until in the final moments they are orbiting hundreds of times a second, and then they slam together in one of the most violent events the universe can produce. Those ripples in space are called gravitational waves, and they were predicted by Albert Einstein over a century ago. For 100 years, they were just a theory. Then, in 2017, humanity detected the gravitational waves from exactly this kind of event, two neutron stars colliding, stretching and squeezing the entire Earth by less than the width of a single proton as the waves washed over us. And this time, we did not just feel the collision. We saw it too. Telescopes all over the world swung around to catch the light from the crash in a nearby galaxy. For the first time in history, we had felt an event through gravity and seen it with light at the same time. It launched an entirely new era of astronomy. And what those telescopes saw in the wreckage changed everything. When two neutron stars collide, they blast out a cloud of debris, and in the insane heat and pressure of that crash, the heaviest elements in the universe are forged. Gold, platinum, silver, uranium. Scientists estimated that this single collision created several Earths' worth of pure gold, flung out into space in an instant. These crashes are one of the main factories in the universe for the precious metals we treasure. So think about that gold, drifting through space for billions of years, mixing into the cloud that would one day form our sun, our Earth, and everything on it. Which means the gold in a wedding ring, or a necklace, or a watch, very likely began its existence in the collision of two dead stars, long before the Earth even formed. Your jewelry is, technically, pre-owned. The previous owner was a neutron star, and it is billions of years old. There is one last thing a neutron star can teach us, and it takes us right up to the edge of the known universe. We have seen that a neutron star supports itself against gravity by packing neutrons as tightly as possible, but there is a limit to how much even neutrons can take. If a neutron star gathers too much mass, somewhere around 2 to 3 times the mass of our Sun, then not even that wall of solid neutrons can hold the line. Gravity wins again. The star collapses one final time, past the point of any return, crushing itself down toward a single point. And in that moment, it becomes something even more extreme. A black hole. That is what makes neutron stars so special. They sit right on the border between the two greatest extremes in nature. On one side, ordinary matter, atoms and light. On the other, the black holes, where matter and light disappear entirely. A neutron star is the very last thing that manages to stay on our side of that line. The final outpost, before the darkness takes over. And what happens on the other side of that line, inside a black hole, is one of the greatest mysteries in all of physics. It is a story so strange, so mind-bending, that it deserves a whole video of its own. And that, my friends, is exactly where we are going next time. So let's take one last look at these incredible objects. Born in the fire of a supernova, a whole sun crushed into a city, a spoonful that weighs 1 billion tons, spinning hundreds of times a second, sweeping the galaxy with lighthouse beams, wrapped in magnetic fields that could tear you apart from the distance of the moon. And when two of them collide, they forge the very gold we wear on our fingers. The neutron star is nature at its most extreme, a dead star that refuses to fade quietly, and instead becomes one of the strangest, most powerful objects in all of creation. Not bad for something you could drive across in under half an hour. Here is tonight's one question. Where did most of the gold on Earth originally come from? 1. From the Big Bang, at the very birth of the universe. 2. From nuclear fusion deep inside our own sunday. Or 3. From collisions between two neutron stars. The answer is 3. The Big Bang made almost no heavy elements, and a star like our Sun only ever fuses the light once. Much of the gold and platinum in the universe was forged in the violent instant when two neutron stars smashed together and flung out across space. So the gold in your ring is, quite literally, the treasure of a dead star. And that brings us to the end of today's journey into neutron stars. A whole sun crushed into a city. A single spoonful heavier than all of humanity, spinning hundreds of times a second and forging the gold we wear on our hands. For something left behind by a dying star, it really is astonishingly full of life. So here's my question for you. Now that you know what they really are, would you want to see one of these tiny, impossibly heavy stars with your own eyes, just once? Let me know down in the comments. Thank you so much for watching all the way to the end. If you had fun, or you learned something new today, please consider subscribing. Next time, we cross the line that even neutron stars cannot, and step inside the strangest object in the universe, the black hole. So, until next time, I will see you in another world.